us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. So in this specific discussion, we're going to do is the last bit about the concept of isochoric heat capacity, and it's going to follow up our first video we have done on this specific aspect of isochoric heat capacity. And that was basically a representation of our heat capacity in terms of our partition function. And of course, we have looked at some of the steps which we have done through, of course, substitution and finding various ways of representing this specific heat capacity in terms of a partition function. Now, in that discussion, maybe we can just have a short recap. And mentioned that we can have the heat capacity given in terms of the ratio between, or the derivative with respect to temperature at constant volume given as such, which is a derivative of internal energy with respect to temperature given as such. And then we said that we had found a derivative, or rather a derivation of the partition function of internal energy represented using the k bit, or a representation of the partition function or internal energy in terms of the partition function given as k bit t. And of course, this was given as the derivative of the natural log with respect to temperature at constant volume given as such. And we said that one of the ways in which we can represent these isochoric heat capacities as a substitution of this specific numerator, whereby we said that this basically is going to be given in terms of, so let's call this one equation 1, and then we're going to derive another equation from this, considering this second aspect as this kBt, the square of that one, and then we're going to have the natural log of Q with respect to temperature V. And this is going to be given as this one all over. So I've done a substitution basically of this specific section for you. So we're going to have this one over dt, and this is going to be given in terms of that one and a constant volume as such. So then therefore we're going to just have a look at these two specific sets, and we had mentioned the concept of finding a derivative of a product, whereby we had said that we can find, this representation is correct, so we have this one given as d over dt constant volume. So we had given a derivative over this specific heat capacity in terms of CV, which we said we are going to use the product rule by holding one factor constant and then differentiating the other, and then differentiating the one that was held constant, and of course holding the second factor constant. And that was the product rule for derivatives, which we had mentioned that if we have a uv given as such over dx, we're going to have this one as ud v over dx plus v du over dx given as such. And of course, I elaborated on that specific representation. So therefore, I'm going to skip that one. So in this case, I decided that we can consider this specific factor as v and u, and this one in the bracket with respect to constant volumes is so this perhaps u v given as such, which are two factors which we need to differentiate with respect to temperature. So the first one, we're going to consider temperature, whereby we're going to have kBt. So this specific coefficient has been taken from this particular point, so we're going to have 2 kBt as one of our factors, and we're going to hold this second one constant as the natural log of Q with respect to temperature as constant volume, and then we're going to have that one the sum of, so we're going to hold this one constant which was differentiated in the first factor, and have k be the square of t, and differentiate the second one. So this one is going to be a second derivative of the natural log of Q over dt, the square of that, and this one is going to be under constant volume given as such. So this is the first representation we had on the aspect of the isochoric heat capacity. And as we can see from the various aspects of our thermodynamic quantities which we have done in terms of the partition function, these are only unique in a sense that we're going to consider the, of course, second derivative of that specific partition function using this product rule. Now we can define this specific aspect of the isochoric heat capacity in terms of an ensemble average, where we're going to have, so I can just do away with this. We were after that one representation for from our previous discussion. So we can find this isogoric heat capacity in terms of an ensemble average, whereby we're going to have CV represented as a derivative over dt. Now, now this specific internal energy, which was U, therefore is going to be given in terms of an ensemble average, whereby we're going to consider, we have come across these specific representations for internal energy. We're going to consider that one given in terms of an exponent of this negative ui over k dt. And then therefore, this is going to be over the summation from I over an exponent negative, this is ui over k dt given as such. So this is going to form what we refer to as an ensemble average. And of course, from their specific definition, we're going to see that the heat capacity can be represented in terms of a simplified form of a CV, which is equivalent to U squared minus U, the square of that. And then this is going to be over kBt and the square of that. So in this case, these two specific representations from statistics are going to give us a specific meaning, whereby we're going to see that basically they represent the various averages that I've mentioned. And this collectively are going to assist us define the concept of isocolic heat capacity in terms of an ensemble average, or defining this specific internal energy aspect of this derivative as an ensemble average. And that, therefore, that's going to give us a different derivation of this specific aspect of isochoric heat capacity. And in this case, I've mentioned this particular concept. So we're going to have this one given in terms of a square, and that basically represents the mean squared internal energy given in this specific order. And then we're going to have this second one given as this one. So this is the mean. So that one represents the mean squared internal energy. And the lower one is represents the square of the mean internal energy, which is the square of the mean internal energy given as that. And the two are going to give us a representation, of course, for those two specific aspects. Now, in this case, I'm not going to go into details of these two specific representations, but as we are going to come across them, we're going to see that we can consider this aspect of an ensemble average, which I've mentioned in representing this specific aspect of course, the variables in thermochemistry. And of course, I'm going to discuss that one in a different video concerning those ensemble averages. So in this case, I'm going to leave it there. Kindly check our description boxes for various links of other videos which are related to this, and they are going to assist us understand the various aspects of thermochemistry. Now, I'm going to also to put a link of other similar videos in terms of perhaps a playlist. Kindly check and also engage us in the comment sections for more. So that is it for now, guys. Bye, God bless. We'll catch us in our next video.